can start now. Yeah. So, good afternoon, everyone. It is my pleasure to announce a talk by Emanuela Gussetti from Bielefeld University. Emanuela works with Martina Hofmanova on her PhD project, and she obtained already very interesting results on an approach which is, say, quite new to stochastic partial differential equations using the so-called rough paths. And I think the results are very interesting. So please, Emanuela, please start.
Thank you for the invitation and for the very nice introduction. Today I will work I will talk about a joint project with Antoine Roquet at TU Berlin concerning pathwise approach to the stochastic Landau-Lifschitz-Gilbert equation in one dimension, on one-dimensional domain in particular. We will work in this work on torus. Okay, so what is the subject of this talk? We start first on the deterministic model. What is the Landau-Lifschitz-Gilbert equation describing? The Landau-Lifschitz-Gilbert equation describes the magnetization of a ferromagnetic material, for instance, iron, cobalt, or nickel. And in particular, we are looking at the contribution that come from magnetic phenomena that are included into this magnetization. We have to think at ferromagnetic material, for instance, as a piece of iron that is divided in domains. In each domain, there is an orientation of the magnetization, and we see magnetic contribution at different levels, so macroscopic, mesoscopic, and microscopic level. At the macroscopic level, between these domains, there are some different orientation, and so there is some exchange of energy. At the mesoscopic level, we can look at atoms that have different, the nuclei have different orientation, and this generates some magnetism in that with this discrepancy in the orientation. Then we can look at the flow of electrons from one atom to the other, and this is also generating a magnetic field. And at the microscopic level, the electrons themselves are generating some magnetic phenomena. And all of these phenomena, so macroscopic, mesoscopic, and microscopic, are all included in the magnetization. We can look now at the equation that was derived by Landau-Lifschitz and then Gilbert, where there were some, let's say, the only difference was in how one can write down these constants. And we can look at the solution to this equation, that it's an equation that evolves in time, in space, and takes values on the sphere. So we have some spherical constraint in the equation. And this is the sphere of R3. In particular, in this work, we will be working on torus in one dimension, but the results can be extended to bounded one-dimensional domain with non-Neumann boundary conditions. This sign denotes the cross product on the sphere. So if we have M that goes in this direction, H that goes in this direction, M cross product H will be orthogonal to the plane generated by the two. And we will use it throughout the talk. And all of the magnetic phenomena we have described before are somehow, the physics is encoded in this term H that is describing the total energy. In this talk, in particular, we will look at the exchange energy. It is a quantum mechanic phenomenon that cannot be described by classical physics. And it has the form of a Laplacian, so it's some kind of diffusion. In particular, I want to stress now that the deterministic model is phenomenological, it's a phenomenological equation. So it comes basically from rigorous derivation from physics laws. And now we will turn to the stochastic equation that is no more phenomenological, but it's validated by some physics paper and experiments. And we somehow decided to include the noise in order to model thermal fluctuations. Thermal fluctuations are very important in the field of magnetization, and therefore it's necessary somehow to see how they interact with the equation. And in physics, they include the space-time white noise. So this equation is no more phenomenological, but it's validated by experiment, and it's meaningful to put here multiplicative noise of this form. In this talk, we will not use the space-time white noise, but we will use Brownian motion in time with a smoother spatial dependence. So we will have something like that, W2 infinity for the spatial component. How are we interpreting the noise? Somehow, here I'm writing derivative of Brownian motion, but it really doesn't make sense. And the motivation is that also if we consider Brownian motion, we have that every path is 1 alpha minus Holder continuous. Okay, but the problem is that it's almost everywhere not differentiable. So somehow we cannot really use classical integration theory to define an integral of the Brownian motion. So we want somehow to give a meaning to the multiplicative integral that we have seen before. Here I dropped the cross for simplicity, so we can look at this integral like this. So we have two integrands. And yeah, we know that we have a theory of integration that tells us that if the integral is beta Holder continuous, and what we integrate against is alpha Holder continuous, and the sum of the two exponents is strictly bigger than 1, then we can employ the so-called Young's integration. But when we look at stochastic partial differential equations, we never expect the time regularity of the solution to be higher than the regularity of the noise. And therefore, we expect actually also the solution to the LLG to be 1 alpha minus Holder continuous. And we know that Brownian motion is 1 alpha minus Holder continuous. So if we sum the two, we don't get that is strictly bigger than 1. And so we cannot employ Young's integration. And so we, okay, in a stochastic analysis, people came up with 2 types of integration. So Stratonovich and Ito integration that are still important also in the framework of Raspatz, and we will see it later. Now I will give you a primer on Raspatz integration. That is the type of integration that we will use in this work. So somehow Terry Lyon came up with the Raspatz that give a more analytical construction to stochastic integrals. And somehow now let's start from a toy example. We take a smooth path. So we take a path defined on time with real values. We can take this to be a C2 bounded function from real to reals. We look at this integration, so f of x integrating against the x. And one way to look at this now is to think maybe of doing the Taylor expansion in f of xr. So we are in f of xr, we do Taylor expansion in xs. So we'll get xs, we'll get first derivative of xs, increment. I will denote increments with this fancy delta. So increment r minus s integrated, and then we have a reminder, some rest. Now we can plug out some stuff. So this is s, and it can go out. Here we get the increment from the integral, and here this can be plugged out. And we get again an integral, and then we have a rest. So we can look at this object and we identify some components. So we have this increment here and this increment here. And we can define these two objects. So let's say I call first iterated integral this increment, and second iterated integral this other integral. And this is our first Ross path. So we have constructed the Ross path. And in this way, we have constructed the Ross integral. So there should be two elements that will substitute these integrals when we have a less regular path, such that we can reformulate the things in this way. And it's important here that there is some kind of rest that has the correct regularity. Still now I'm a little bit cheating because the observers, the attentive observers will tell me, okay, but now you take a path in C alpha, alpha also continuous, so like Brownian motion, and you have not still defined this. Yeah. So now we see what we do for Brownian motions, because if we have a smooth path, then the object is well defined. But if we have Brownian motion, this is the objective of our discussion. I've still not defined this. No. Okay. So if we consider Brownian motion on some probability space that is also adapted, we want to define a Ross path starting from W, which means we want to define a couple X, and that X bold that will be second iterated integral to define the integral. To do this, we have seen before that the first iterated integral was just an increment. So the increment for Brownian motion is well defined, and we can just define it like this. For the second iterated integral, here we need probability. So somehow, in order to construct the object, we cannot use okay, we really need probability because it's not possible to define Ross integral pathwise. We can define only through probabilistic constructions. So we define the second iterated integral associated to the Stratonovich integral for every omega fixed as the Stratonovich integral, where we have afterwards fixed omega. And this is well defined for every omega in a set of full measure with respect to the probability. And this is very important somehow, that we somehow fix a set where the Stratonovich stochastic integral is well defined, and then we will proceed. But this set is very important, that we somehow fix it. But as you know, you would say, okay, you choose Stratonovich, can you choose also Ito as a second iterated integral? Yes, of course, we can also choose Ito as a second iterated integral. And one can have a Ito lift, and in this case, one will have a different set of probability where the Ito integral is well defined for every omega. For the analysts that are here, somehow I didn't forget an omega here. It's really that one is constructing the object probabilistically, and afterwards one fixes omega. I cannot define W omega, dW omega. Okay, so it's really probabilistic construction, and then afterwards we fix the path. So we have constructed two possible candidates for our Ross path, and somehow, what do we choose? Okay, one first is looking at the model. So from physics, it makes sense to study the Landau-Lifschitz-Gilbert equation with the Stratonovich integral. So we will use the Stratonovich lift. From a Ross path perspective, there is a property that is called geometricity that the Stratonovich integral has. And this property is analytically correspondent to the classical rule of calculus. So somehow we know that the Stratonovich integral follows the classical rule of calculus, which translates in Ross path to ask for the so-called geometricity property. So we will choose this Stratonovich integral. One can work with the Ito integral. One will then have other rule of calculus, but I would say that the Ross path theory is particularly strong because somehow we can forget of probability and work like in the deterministic setting. And this is why I was telling you that this set is very important, because from now on, we fix omega in this set where the Stochastic integral exists, such that for every omega that is fixed in this set, this couple is well defined. And we will forget now about probability, and we will work basically like if we were doing PDEs, okay? Because we also have a classical rule of calculus. In the classical theory of rough paths, one sees that if one doesn't take W to be R valued, but with values in R3, the first iterated integral is a vector. And the second iterated integral will be constructed here with the tensor product. So the second iterated integral is a matrix. We somehow reshaped our problem into a more general framework of the so-called unbounded rough drivers that, okay, basically are rough paths with other shapes. So here we somehow we want to reshape our first iterated integral into a matrix. And the second iterated integral is itself a matrix that can be decomposed in a product of two antisymmetric matrices plus an antisymmetric matrix. And this is somehow giving some nice rules of calculus that we need. In particular, what it's very used is the fact that M cross product G times G should be times M should be 0. That is a property of the cross product, and this is somehow reshaping into our framework with a relation of this form. Okay, this is not immediately clear now, but it's not so important. The important thing is somehow that we have built an object that preserves this property, and when we test the equation by the solution itself, we see that the noise is vanishing. So basically, at this 0 level, the equation is like a deterministic equation in a sense, okay? So also when we look at uniqueness, where the drift is not vanishing. I would like to give a small, okay, first we look at definition of solution. What do I mean by solution to the stochastic Landau-Lifschitz equation? We have defined the noise, so now we know everything. So it's an evolution equation defined on torus with values in S2, such that when it evolves, it still stays on the sphere, so it shouldn't escape. We will have L infinity H1, L2 H2 regularity. So L infinity in time, H1 in space, L2 in time, H2 in space. And we also have energy in the definition of solution. So we have basically energy solutions. And okay, now it's a little bit strange maybe for who has never seen rough paths, but let's look at this equality. This is the first iterated integral that we defined before. This is the second iterated integral generated by Brownian motion. This is the Stochastic lift again. And this is the so-called remainder. We say that M is a solution to the Landau-Lifschitz-Gilbert equation if there exists a map, M natural, that is defined implicitly by this equality. So M natural defined as this minus the sum, where the equality has to hold in H-1, but actually it will hold in L2, such that this remainder should be regular. So this is VP variation. So I somehow changed from alpha order to VP variation because in the rough path setting, we normally work with VP variation, but you can really think at alpha order continuity. So this is equivalent to some alpha order continuity with some scaling in 1/3, 1/2, plus the scaling in 3. Somehow, how does it work intuitively? this is giving an oscillation of 1 over p. This is giving an oscillation of 2 over p because we have an integral against the 2 Brownian motions. So it's 1 over p for one Brownian motion and 1 over p for the other. So it's a 2 over p. And here we hide all of the contribution of more, so of 3 over p variation. And this in particular means that we see some kind of oscillation here. Here we see a more regular oscillation, so it's oscillating less. And here we somehow see the constants in a sense. In fact, if you look here, you have VP variation with p bigger than 1, not with q, let's say q bigger than 1, which are constants. So somehow the intuition behind the integral is we look at the rough oscillations that are really giving us some kind of oscillation, and we neglect the others because they are not important for the oscillation, and we put them in the remainder. So to conclude on this definition, this term, it's what makes the study of Rothbard heavy. Okay, so this is the term where one has to work on quite a lot, let's say. Let's go a little bit to see state of the art. I apologize from the pronunciations that, and I hope also I didn't make mistakes. Okay, I would like to speak a little bit about the state of the art and on this equation. So there are results of existence in 1, 2, and 3 dimension through Galerkian approximation and compactness from Brezhnev, Goldys, and Zakai. That was one of the first work on the stochastic equation, maybe the first work. There is another paper that is very interesting from a physical perspective, because they prove existence and uniqueness of pathwise solution in 1 dimensions. And the authors also prove the so-called phenomenon of magnetization reversal. So one has a sphere, and there are 2 equilibrium points for the deterministic equation. But when one is adding a noise, the trajectory that in the deterministic setting would collapse in one of the 2 points undergoes magnetization reversal. That means that it can spin from one pole to the other. So the addition of noise is somehow determining this, this behavior, and this is done also through establishing the large deviation principle. There is another paper of Brezhnev, Mann, and Mukherjee, where they establish existence and uniqueness, also in a 1 dimension of pathwise solution, and they obtain a strong Wong Zakai result. In order to do this, they employ exponential transform and maximal regularity. And in this paper, there are some questions that have been posed. And one question was whether Rothbard's theory could be useful to establish the Wong Zakai, strong Wong Zakai convergence for multidimensional noise, and somehow also without using transforms. And our paper, it's an answer to this paper. So we are answering to the question, and we say, yes, Rothbard's theory can help to establish a strong Wong Zakai convergence. There is another paper that was written by Goldys, Grotowski, and Lee, where somehow they solve the problem that the exponential transform has, because with exponential transform, one cannot consider normally multidimensional noises, but they somehow found a way to treat the multidimensional noises still with the transform. And there are 2 papers actually that are answering to the question that was posed here by Brezhnev, Mann, and Mukherjee. One is a paper of Fahim, Hausenblas, and Mukherjee, where they use Rothbards and then exponential transform. So they really, they are able to transfer the exponential transform technique to Rothbards. In this case, they are not able to use multidimensional noise, and they leave it as a open question, but they are able to establish a strong Wong Zakai convergence. In our framework, we establish existence in one dimension with multidimensional noise, uniqueness in one dimension, and we obtained strong Wong Zakai convergence in one dimension. So somehow the question that was posed by Brezhnev is answered. I would like to stress here that in contrast with Stratonovich theory, we cannot treat cylindrical noise. I mean, I at least have not thought a lot about it, but I think we cannot treat cylindrical noise. So I mean, there is no theory of everything. So there are boundaries. In the paper, we establish also Lifschitz continuity of Ito-Lyons map. That is the map that associates Brownian motion to the Brownian motionless solution, which implies the large deviation principle and the support theorem, also for higher order initial conditions. So up to now, I've spoken for initial condition in H1. Here we can have initial condition for k bigger or equal than 2 also. Okay, let's go and see a little bit of proofs. There are some technical issues. So in the classical Stratonovich and Ito calculus, one would employ a product formula like the Ito formula to consider the squared equation. Here, in fact, we have some kind of, okay, it's not a monotone equation, but it's one can have some monotone parts that one wants to keep on the left-hand side of inequality. So it's meaningful to consider a squared equation. And here one has to derive product formula, but luckily they were already available, so we just employed them. Another part that is a technical difficulty is, as I said before, the estimation of the remainder for the squared equation. That is done through a classical result that is solving lemma. And okay, before we have seen that we derive the integral through a Taylor expansion. But of course, the Taylor expansion is a local thing. So somehow the solving lemma is what is allowing to pass from the local representation to the global representation. So somehow this is why it's so famous and important in Laplace theory. So this is some kind of passage to the global integral. Another technical issue that we find in the proof is that we are considering an initial condition in H1. So we don't look only at the energy at the L2 level, but we have to take the derivative of the solution and look at the energy there. So there we have to test by a squared equation and use the product formula. And we have the corresponding remainder that has, let's say, more terms. And in particular here, the remainder is depending on the drift. Because as I said before, when we test the solution here, the noise is vanishing. Yeah, so we are really in the deterministic setting. But in this case, the noise is not vanishing, so the remainder has to be estimated through the drift that is nonlinear. And so there are some difficulties there. So let's see first the proof of uniqueness. So for uniqueness, we consider two solutions that need to have this regularity. We take the difference of two solutions and we want to prove that the difference, this is standard, that the difference is 0. So we consider the product of the two. And also in this case, the noise term is vanishing because we have these symmetries properties on the noise that we saw before. And basically the proof is like in the deterministic setting. So here we thank the analysts that did it before us. The point is here we have interpolation inequality that holds only one dimension. And somehow there is no uniqueness in one dimension in the deterministic case. Okay, here we are not talking about maybe 2 and 3 dimensions, but somehow one of the things why one cannot exploit the same proof is for more dimension is the interpolation inequality in 1 dimension. And this is for what it is about the uniqueness proof. So we have uniqueness or pathwise uniqueness of strong solutions, provided we have this. Now we can pass to the existence proof that is quite standard. So it's done through compactness. So the nice feature of geometric raspas that are the raspas that have the classical calculus, the classical, let's say, deterministic calculus, is that we can approximate pathwise the Brownian the raspas lift of Brownian motion with the Stratonovich integral by means of the piecewise linear approximations. So it's a very powerful tool because we can really consider an approximation of the stochastic integral. Then we consider the solution associated to this approximation that exists and it's unique from standard results. And then what we want to do is bound it uniformly in some space. In this case, from the 0 level, we just get the solution is in L infinity, so we don't get more. From the derivative level, so we do the derivative of the equation, and we use the initial condition is in H1. We can get L infinity H1 plus some other nonlinearity. And then to get L2 H2, we need to consider an equivalence of the Laplacian on the sphere with some other terms, let's say. And this is needed, this is VP variation with values in L2, and it's replacing the condition that you normally have in Aubin-Lyon to have the derivative of the solution to be Sobolev something. So somehow this is the replacement because we need some regularity in time to use Aubin-Simon-Lyon. And this is for what's about initial condition in H1. If one has an initial condition in HK for k bigger or equal than 2, one can get this was small, it's a typo. So L infinity HK, L2 HK plus 1, and then 1 degree less of regularity for the VP variation. So one from employs Aubin-Lyon, and we have strong convergence of subsequence in L2 H1, plus some continuity in L2. Yes, one has also intersection continuity in L2 here. And same here. Down here, one will have a continuity in HK minus 1. And then one, okay, classically finishes the proof by identifying the limit in the nonlinearities. So this, we have basically done a deterministic proof here. There is no probability popping up because we have fixed the set before. And also, we are not losing any omega during the process. Somehow this is something that in classical calculus, one doesn't know really which is the set of null measure on which things are holding. I mean, it's not really determinant, but it's interesting to notice. We can pass now to what I was saying before, that is this phantomatic Wong Zakai convergence. So what is Wong Zakai convergence? If we have an approximation of the Brownian motion that converges in some norm to the stochastic integral that we have defined, we would like to know if also the associated solution converges to the limit in some space. But somehow you would say, okay, you have said like 3 seconds ago that compactness implies Wong Zakai convergence, because we have said that if we have approximated solutions, approximated noise, then the solution will converge strongly in L2H1. But somehow the point here is maybe to find a stronger convergence. So we would like to have better convergence to this solution in the better space that we can, that is the space of existence of the solution. So we would like to get the Wong Zakai convergence in L infinity H1 and to H2. So this, the better that is possible. To do this, we employ again the pathwise approach that we have employed in existence and uniqueness. So we take the sequence of solutions, again driven by the approximated noise, and M is the limit equation that we have found with existence. And we would like to prove this convergence, so that this is L infinity H1, L2, H2. In particular, what we will prove is the so-called continuity of the Ito-Lyons map. That means that the map that associates to the Ross path to the solution is continuous. And we will prove in particular Lifschitz continuity. And this is somehow one of the strong features of Ross paths. So because now you might not see this, but once one has the continuity of this Ito-Lyons map, one can like prove straight away directly support theorem large deviation, but really without doing the proof, because it's hidden into the continuity of the map, the possibility of having these two results. And this is one reason why if one needs something like support theorem of large deviation, if one can prove the continuity of the Ito-Lyons map, let's say these theories can be very powerful, depending on what one has to do, of course, and if one can apply it, that's another thing. Okay, let's see something. So in this case, we want to prove convergence of Mn to M. So we take the difference of the two, and we define the difference variable, that is the zeta variable. We take the derivative of it. So we take the derivative of the equation, and we use the product formula that we introduced before to define, and we look at the remainder term of the squared equation. So we have the product of the two, we have the drift, and we have some terms that depend on the noise. So there will be the noises, the not approximated noises and the approximated noises. This will depend also on the solutions, of course. And here the drift is the drift of the derivative. So we have some, oh no, the drift, yeah, it's the drift of the derivative. So we have nothing strange, it's just derivative times derivative there, okay. In order to estimate this guy, we apply the so-called solving lemma, that is from local Taylor expansion to global approximation. And what we notice is that we can somehow rewrite everything as differences that will make the convergence occur. So somehow we can get the difference of the noises. And this is something that it's, let's say, a control that you can think about like T minus S. So a difference in time, you can think it like this. And it's somehow depending on it's also depending on the noises. And here the constants needs to depend on the initial conditions, some powers of the initial conditions. So if one then wants to go to some stochastic estimate, one has to impose some conditions on the initial condition, some moment conditions. Another thing that we notice here is that in the remainder we see the drift that is appearing. So, and the drift is not linear, so this is somehow the part when one has to be careful in the estimation of this term. And okay, one then gets L infinity L2 and L infinity L2 here, and this will be bounded by initial conditions. So we will get in complex after applying the Rask-Gromval lemma, that is basically a Gromval lemma for Roth paths. In total, we will get an estimate that is like an exponent that depends on time and depends polynomially on the H1 norm of the initial conditions times the initial condition. And here again, same constant. Maybe there is also here an exponential. Yeah, maybe I forgot here an exponential. That will depend on time and on again on polynomially on the initial condition. So and from the differences, let's say. So if the initial conditions are converging and noises are converging, this in particular implies that there is a convergence in infinity H1 and to H2 of the approximated solution to the LLG to the solution. Yeah. And so somehow this is not only continuity, but it's actually Lifschitz continuity, local Lifschitz continuity, local in time. And this basically implies with nothing, no work, large deviation principle and support theorem for the law of the solution. And really the proof is like in the SD setting, because it relies only on continuity. Further developments, maybe I have already discussed with Professor Goldys about existence maybe of invariant measures for this process, Gibbs measures, and yeah, maybe more dimensions. And yeah, thank you.
Thank you, Emanuela, for a very interesting talk. Are there any questions? So maybe I will ask, it's a question or comment. What is surprising here is that you can do something that it's quite difficult when you use Ito approach. So you use Aubin lemma for every omega separately. Yes.
Yes.
Yeah. So your subsequence, which comes from compactness, it depends on omega, but this it's not a problem for you. Yes.
I tell you why it's not a problem, because we have uniqueness. It's not a problem because we have uniqueness.
Yes.
If we have not uniqueness, it's completely a problem, like in 2 dimensions. Yes.
Oh, yes. But in Ito approach, you would have immediately problem even with measurability. Yes, and here you don't have to worry about that at all. And so this is very nice.
Yes. It's from the continuity of Ito-Lyons map. So you do everything, and then you, from the continuity, you get measurability with respect to the noise. So somehow, yes.
Are there any questions? Any more questions? Oh, yes. Daniel, please.
Yeah, I have a question. So just on the slide, you mentioned that, so the inequality below on Z, the infinity norm. So you follows from a Gromval type lemma. So you can conclude from the sewing lemma, which tells you something about the integral of cost. So there is a Gromval version of the sewing lemma, because the sewing lemma is not the usual integral. Again, there you speak about the germ and so on. So is there something yes, or did I understand you wrong there?
There is the so-called Ross-Gromval lemma, that is a Ross version of the Gromval lemma. And yes, it's in a paper of Gubinelli, of Manova, Deja, and okay, I don't remember now. But if you want, I can send you the paper if you need it.
Yeah, that's very interesting. Please, yes.
Yeah. Just send me an email or text me your name. And
yeah, okay. I will.
Are there any more questions? Yeah, if there are no other questions, then let me close the meeting, and we can meet in a few minutes at the coffee break and to talk more about mathematics, and not only about mathematics. and we will start it in a few minutes. So now, thank you very much. Thanks, Emanuela, again for your talk. Thanks. Okay, so I will close the meeting.
Thank you.
Thanks. Bye. Bye.
Bye.